Okay, we just finished up lesson 1 in the previous video in 1.3. So now we're going to do 1.3b. This will be a little bit quicker than the last one. Was a little lengthier. We had a lot going on there. But let's take a look at here multiplying radicals. So we talked about addition and subtraction where the index and the radicand both have to be the same. The multiplication of radicals and the division, same thing. Not as much has to be the same. So in other words, the radicand doesn't need to be exactly the same, but the index has to be the same. So that's the key on this is we got to make sure it's the same index for us to be able to multiply. Otherwise, we have some issues. Now, there's some ways around it a little bit. If the bases are the same and the indices are not, we can work around it a little bit using rational exponents, but we're not there yet. Okay, so right now we just want to multiply these if it's possible. So what we want to do is just look at single radical multiplication, and we look at like these two, and we go, well, the first question is it even possible to do this? Well, they're both square roots. So what we have is what's called the product property of radicals. And the product property of radicals simply says if you have two radicals with the same index, you can sort of squish them together. Now, what I would recommend is don't literally multiply them just yet. I'll show you why. Okay, but that's what we're doing. Is we're doing 5 times 15, which is 75. You could do it, but with bigger numbers or multiple numbers that we're multiplying factors. Remember, what we're going to do is, aren't we going to break these down to figure out factors anyways? So we just did. Like these are two factors of 75. So we're going to have to break them down anyway. So you might as well just leave them at least that part factored. So if the indices are the same, we can switch them together. Now, the reverse is also true. If I have a single radical and I want to split it up, then what I can do is I can split this up as long as the indices are the same for each factor inside of the radical. Okay, can't do that with addition and subtraction because you cannot take a radical across the plus or minus sign. So help you God, you'd owe me soft snickerdoodles, just like exponents. So here what we want to do, though, is we can break down 15. And what you'll notice is I can take a 5 out, but I left a 3 behind. And so we just look at simplifying when we're done. And so I leave them factored out like that. The cube root of 9, the cube root of 6, I can definitely go ahead and they have the same index. And what I'm going to do is leave it out like this. So I know I have 3 2s, or excuse me, 3 3s from those two. And so I can take a 3 out, and I left a 2 behind. Now, again, watch your index. Don't leave it like this. That's a square root, and we're not looking for a square root. We're looking for a cube root. If it's a combination of the two, what you want to do is just sort of put the two numerical values next to each other. So again, I don't typically multiply them, not necessarily, but I do maybe with the variables. So like x times x is x squared. So multiplying powers, you add exponents. Now, the reason why I do that is now with 8, we have what, 3 2s again? And then with 10, we have 5 and 2. And we're putting things in groups of 2. So I can take 2 2s. 2 times 2 is 4. And I left a 5 behind. Now with my x's here, I have 2. And so 2 divided by 2, how many I have divided by my index, is 1. Okay, this is great. This is great. Now, normally, okay, I would say, oh, you want to be very careful because in the last lessons, we talked about when you go from an even to an odd, you need absolute values. But in this problem, we don't need to. And you're like, what? And this is what makes math so frustrating but beautiful at the same time. Why wouldn't it not need an absolute value? I mean, we did go even and odd from this intermediate step to here. And I sort of emphasize intermediate for you. It's because when we go from even to odd, it needs to be from the original to the end. So this is an intermediate step. I look back at the original. Did I go from an even exponent of x's to an odd? No, my x's are odd. Now the question is, why does that matter? And so ponder on that for a moment, pause the video or whatever. Why is it that I can already assume that x is positive from this original statement? Because I don't need absolute value, so I have to assume x is non-negative. And the reason that I can assume that is because I cannot take the square root of a negative and get a real number. So whatever's inside of a square root, I have to assume to be non-negative. Well, 10 is positive, so x cannot be negative. Otherwise, I'd have a negative inside. So x is then implied to be positive from that point forward. And so that's why we don't need absolute values on this one, unlike ones where, now, if we started here, if this was the first thing I gave you and you went here, then you would need absolute values because we can't assume x. We have to assume x is positive or negative. It doesn't imply that it's positive in the case like that. So always go from the beginning to the end when you're looking at even odd, beginning to end. Now, let's keep moving with some multiplication. That was a single term. Let's look at two terms. So we're going to FOIL. Keep an eye out for like conjugates. That makes your life a little easier. So like the first one, notice these two are conjugates. And so when we talk conjugates of FOIL, the outer and inner cancel each other out. And so we just need to FLE this. And so when we talk about foiling, first, outer, inner, last. Now, I'll show it to you. I'll show you all four of them. But the outer and inner are going to cancel each other out when they're conjugates, okay? And so we want to make sure that we understand what is a conjugate, and we'll be definitely using a lot of conjugates. But I'm going to do all of them, and I want to show you this. So because these are what we call conjugates, I only have to do FLE rather than FOIL. But let's do all four, and I'll show you why. So square root of 3 times square root of 3 is square root of 9, which is 3. So that works with square roots. Okay, square root of 4 times square root of 4 is 4. Square root of 7 times square root of 7 is 7. Square root of x times square root of x is x. And so square roots work really nicely like that. Then I'm going to get, so I have first, then I got outer, and so that is a positive square root of 3. Then I've got inner, which is a negative square root of 3. Okay, let's just pause here. Do you see what's going to happen? See, there's my outer and inner. Aren't they going to cancel each other out? When the two-termed expressions are conjugates of each other, that's always going to happen. The outer and inner terms are always going to cancel each other out. Okay, so that's why we can just FLE it rather than FOIL it. Saves us some time. And then you get minus 1. So these two, goodbye. They go away, and I get 3 minus 1, which is 2. That's really interesting. We started with a bunch of radicals and ended with no radicals. Okay, that's something you want to throw, keep an eye on. That's coming up in a lesson here when we do division in just a moment. Now, let's go ahead and FOIL like normal. These are not conjugates, so I don't have a choice. I can't just FLE this. Now, let's go back here and just FLE this thing. So square root of 3 times square root of 3 is 3, and then negative 1 times positive 1 is negative 1. You can see we're still going to get 2, but they have to be conjugates. So I'm going to do first. So I get the square root of 15. Outer, square root of 5. Inner, so we can multiply inside radicals with the same index. So I get minus the square root of 6. You multiply coefficients together, you multiply the radicands together when you multiply radicals. Then you get negative 1 square root of 2. Now you look to simplify, and in this case, square root of 15, we look, there's nothing there to take anything out. 6, same thing, 5 and 2, they're all simplified. So in other words, I can't make any of these what we call like radical terms. We're done. That's as far as you can go. That is simplified. Okay. Looking at the bottom one here, same thing. Square root of 7 times square root of 3 is the square root of 21. I'm going to go a little quicker here. Square root of 2 times square root of 7, square root of 14. Then what we got is negative square root of 2 times square root of 3 is negative square root of 6. And then square root of 2 times square root of 2 is 2. Don't forget negative times a positive is negative. I look to break these down. None of these can be broken down. That's similar to the one we just did. That's as far as I can go. Okay, let's take a look at some radical stuff now. And so first off, the quotient property of radicals. And remember, these properties go in both directions. Remember I said you can either push radicals together to multiply or split them up. In this case, same with radicals. Now, this one's going to come in handy. So when we see a fraction inside of a radical, one option we have is to split it up. Okay, but there are times where putting it back together, so in other words, it's already split up, but it may be advantageous to put it back like that. And I'll show you an example of that where you squish them together. So that's at the bottom of the screen. So let's see a couple of examples. So how do you fix a problem of having a fraction inside of radicals? We cannot have a fraction inside a radical. We're going to use the quotient property of radicals and split it up. And so what we get is the square root of 100 over the square root of 9. The square root of 100 is 10. The square root of 9 is 3. And there's our answer for that. Same with the square root of 1/9. Square root of 1 over the square root of 9. Square root of 1 is 1. Square root of 9 is 3. And there's our solution. So splitting it up, definitely helpful. Squishing it together. Now this takes a little bit of time and a little bit of recognition. And so some practice will help. But what I've noticed here is 48 divided by 6. And x cubed and x. There's some things here I can work with. So why don't I go ahead and write this as one big fraction rather than two separate radicals, one big radical with a fraction inside. Now, I know that's like, wait a minute, you said no fractions inside. That's true. But notice what's going to happen here. 48 divided by 6, 8. Okay, it goes out nice. X cubed divided by x. Dividing powers, subtract exponents or reduce. So we get here. So notice by rewriting it and just simplifying my fraction first, not my radicals, then I have simply a radical that, is for the most part pretty nice for us to jump in on. So we end up getting 2x square root of 2. Breaking down the 8, I can take a 2 out, left a 2 behind. Now the question is, I did go from even to odd here, but that's not where we look. We always look at the original and go, is my x exponent even or odd? And it's odd, actually, in both of them. If it's even in one and odd in the other, the odd is going to trump the even, because even we don't know, the odd we know, because there's no way to take the square root of a negative. So even if this was an even exponent down here or something, this simply is I have no idea. I have to assume it could be either one, so I got to make sure it's positive. This one is, oh, I know right now that x has to be positive or I can't even start the problem. Okay, so just some things to think about, but start, end. Index is the same, we're good to go. Here's another one that if I squish together would make my life a lot easier rather than what we're getting ready to go into, which is rationalizing. And so I get here, and the reason is because 150 divided by 2 is 75. And just like the last one, I get to this point, and now I can go ahead, and 75 goes to 25 and 3, like 3/4. So I can definitely take a 5 out, and I left a 3 behind. And then I can take an x out. Now the question is my x, go from even to odd? It goes odd to odd, so we're good on one like that. So splitting it up also creates an issue, though. Okay, so when we split it up, we create a radical in the denominator. Now, the ones that we just did, the examples we just did, the radical in the denominator went away because we were able to get rid of the denominator through just the fraction itself. But what if we had a problem, let's say, like these at the bottom of the screen, where even if I wrote it as one single radical, it doesn't really help a whole lot because I can't simplify 2/3. Like the 3 is there forever and ever right now. And so I'm like, well, okay, that doesn't really help me. So I don't want a fraction inside of a radical. Sometimes we will, but to remedy that, we will split it up. So that's where we get like the square root of 2 over the square root of 3 or these other values there. Now this should already be in your notes up top. This is just a reminder of what makes a radical simplified. Now we're going to use this process called rationalization. So we're going to rationalize the denominator. Now it doesn't have to be the denominator. You can rationalize the denominator or the numerator. We're just mainly focused on denominator right now. So please, it's the same thing for numerators. You will do that in calculus. You will rationalize numerators. I will ask you a question on the pre-calc exam that has you rationalizing numerators. So don't assume it only works for denominators. It is something that we will use for denominators primarily, but also we'll use it for numerators as well. Now, when it's a single term, and this is where when they're square roots, you guys are going to do great. You have no problems whatsoever. It's just when the index changes do I see some issues with my pre-calc kids. And so in a problem like this, rather than just going, oh, square root of 3 is in the denominator, and I don't want that radical there anymore, most students are just going to multiply by a square root of 3, and they don't think about it because they've sort of memorized that process. And that's fine for square roots, but doesn't work for cube roots or any other index other than 2. So what you want to do is I think you should ask yourself the question, what do I have? What do I need? What do I have? What do I need? The reason is this. The idea of rationalization is simply getting rid of the radical. Now remember, when we get rid of radicals, so like let's say square root of 4, doesn't that just go to 2? There's no more radical. So to get rid of a radical, we need the inside to be a perfect square. So we need perfect groups. So there's nothing left inside the radical. So here, 3 is a lonely 3. What do I have? I have 1, 3. What do I need? Well, if I had one more square root of 3, that means I would have 2 3s, which means I have a group, like the square root of 9. Now remember, to keep this thing, the math properties all in line, we got whatever you do bottom, you got to do the top. Square root of 6. Now on the bottom, what we get is the square root of 9 when we squish those. And you guys probably know the square root of 9 is 3. Square root of 3 times square root of 3 is 3. Or you can look at it like simply just grouping my 3's. I mean, that's what we were trying to do. So what do I have? What do I need? Square root of 8, you can either ask yourself, what do I have? What do I need? Or you can simplify right now. I don't know. I think either way is fine. I'm going to simplify. I'm going to take a 2 out and left a 2 behind. That allows me to at least make things a little bit. So you could go here. Now, I'll show you what to do here in just a moment is if you didn't do it this way. But now what I can say is, well, what do I have? I have 1, 2. I need one more 2. It needs to be in a radical for this thing to work. And so 6 times the square root of 2, can't multiply those two. And then what I have on the bottom is 2. Sorry for squishing there. And so square root of 2 times square root of 2 is the square root of 4, which is 2. Now, let me show you another way of doing this. Let's say I just left it as the square root of 8 and I ask myself, what do I have? What do I need? So what I have is I have 3 2's. You want to go down to its primes. What is 8 made up of? That's what I mean by what do you have? Okay, I want to know what it's made up of. Okay, now what I'm doing is I'm trying to put things in groups of 2. Well, I have one set here. So in other words, it's a little bit like having 3 friends and your parents are like, wait a minute, you will not be able to leave the house unless you have everyone's going with you. Right now, only these 2 are going to be able to go and one has to stay behind. And what I mean by getting rid of the radical or rationalizing is you need to make sure every factor leaves the radical. So we need another square root of 2. So that gives those 2. So what we have is 2 and a 2, or 4 on the bottom. Gets rid of the radical. Square root of 16 is 4. And on the top, we have 12 square roots of 2. And then what we can do is we can do there, and then we get 3 square roots of 2, okay, as our value on one like that. And so I think we had 6 square roots of 2 over 2. You could have simplified that one down to 3 square roots of 2. I'm not sure if I did that when I did the other method. The last one really quick, what do I have? I have 1, 3. What do I need? I need one more 3. And so I'm going to do another square root of 3. And I get 5 square roots of 3 over square root of 9, which is, 3. There we go. And that's called rationalizing. Okay. When it's 2 terms, okay, when it's 2 terms. Now, I do want to show you what do we do when, really quickly, let me go back to this really quick. What do we do if the index is not a 2? Let's say it's a 3. Okay, I've been talking about how this is sort of the whole point. If it's a 3, what do I have? I have 1 3. What do I need? I don't need one more 3. I actually need 2 more 3's because I need a group of 3. Now, it's not a square root, it's a cube root. We got to keep the index the same or we can't multiply. Now, the square root of 3 and 3 is the same thing. Let's write it a little cleaner, is the square root of 9. So I'm going to multiply the top and bottom by the cube root of 9. So I get 5 cube roots of 9. And on the bottom, what was I trying to make groups of? 3. So that's why it's so important for us to understand what's a single term. It's what do I have? What do I need to make perfect groups? Not just some blanket, I'm going to multiply by whatever that radical is and call it good. Because if you did 5 over the cube root of 3 and you multiplied the top and bottom by the cube root of 3, you haven't gotten rid of the radical in the denominator because it's the cube root of 9. That is not simplified yet. I mean, like there's no groups. So make sure that you're asking yourself those questions. Square roots, I know you can get away with it, but cube roots, fourth roots, fifth roots, anything, and that's why we're learning it in pre-calc, is because we got to go deeper. We got to know more than just the basics. The very last thing we do to rationalize is going to be when it's 2 terms. To me, I call this a no-brainer. You don't have to think much. You multiply the denominator and numerator by the denominator's conjugate. And I used that word earlier. Now it's going to be in your notes. So con and then J U G A T. So conjugate. So the conjugate of A plus B is A minus B, and the conjugate of A minus B is A plus B. So you might have even done this in grade school, to be honest. I don't know if they called it conjugates, but I know that's theirs, comparing. So these are not opposites. Those are not considered opposites. They're considered conjugates. Opposite would be like negative A minus B, like it'd be the opposite of both of those. Now, how we use conjugates right here is now I have 2 terms. So I don't ask myself, what do I have, what do I need? because it's not one term. I have two terms. It's a no-brainer. Just use the conjugate. So 5 minus the square root of 3. Whatever you do the bottom, make sure to do the top. Now, my recommendation is don't distribute the top just yet. So in other words, leave that 7 out. On the bottom, because they're conjugates, you don't need to FOIL because the outer and inner are going to cancel out every single time. So all we got to do is FLUH. So 5 times 5 is 25. Positive times a negative is negative. Square root of 3 times square root of 3 is the square root of 9, which is 3. And so we get 7. And I'll probably end up distributing the 7 here in just a moment, but for right now, let's leave it right here. And then I get 22. Now, the reason I don't distribute just yet is, let's say this was 21. Okay, so let's say in 22 is 21. Then I can cancel the factor 7 and the cancel factor of 7 in the 21 and reduce this down. So I don't like distributing it just yet. I think that's a wise thing. And again, that will help you tremendously when you guys get to calculus, because we end up using this technique and we want to leave things written like this for simplification purposes. So might as well get in the habit of it, but there's nothing to cancel. So if you want to go ahead, let's get this thing without parentheses. And so I'm going to distribute that 7. And so 7 times 5 is 35. 7 times negative 1, there's a 1 there, doesn't go inside. And there we go. We're done. Looking at the next one. And again, you can work these and check them, pause it and work them. But we're going to use the conjugate because it's 2 terms. Anytime there's 2 terms, it's a no-brainer. Whatever you do to bottom, you got to do the top. And again, the top, I'm going to leave the 3 out just for a moment. I want to see what happens on the bottom. Oops, gotta get my radical there. There we go. On the bottom, I know they're conjugates, so I'm going to FLUH. Saves me a little bit of time. Square root of 5 times square root of 5 is 5. Square root of 2 times, or excuse me, negative times a positive is negative. It's always going to be a negative. Square root of 2 times square root of 2 is a 2. Ah, look at that. Okay, isn't that just a 3? Now I can cancel vertically those factors of 3, and I'm left with the square root of 5 plus the square root of 2. That's why I leave it out there. That's a great example of that. Okay, there we go. So again, doing the last one, I'm going to erase all this. And so again, if you need it written down, you might pause it right now. Okay, so looking at the last one here, again, the issue is I have a radical in the denominator. And as soon as you hear radical in the denominator, you want to think rationalize. And with a 2 term, it's a no-brainer. Use the conjugate. I'm going to leave that 8 out for right now just to see what happens. We've seen one where it didn't make a difference. I saw one where it did make a difference. And then what we do is FLUH. So we have 16 minus 5. And how I got that is 4 times 4 is 16. Square root of 5 times square root of 5 is the square root of 25, which is 5. And now what we have is we have 8. And the bottom's going to be 11. So you can see I can't cancel 11 and 8. So I'm going to distribute the 8 through. And I've got my 11 on the bottom. And there we go. Rationalizing. So that's going to be lesson 2. Lesson 3 is going to be rational exponents. That'll be in the next video. This should get you going on that part.